But if our process is important, basically lanthanoid, and which has very complicated structure, a complex atomic structure, and resulting very dense forest in absorption line of optical UV. And so compared to usual supernova modeling, opacity seems to be much higher, and it's lead to much longer time scale and dimmer emission compared to original estimate. So originally people thought this event is 1,000 times brighter than nova. That's why kilonova. But after that, you find emission seems to dimmer, so people tend to hesitate to say now kilonova. So now people say macronova or kilonova. Okay. So basically, this case time scale is okay. Also, diffusion time scale is and equalize this with elapsed time, you can estimate when most photon escapes. And the point basically when macronova peaks, and this could be about 10 days also for parameter of and this one is expected about energy deposition rate is something like 40 elks per second. And if you consider at 200 megaparsec, about 22 magnitude emission expected.
Are you assuming a spherical expansion?
Yes.
Is that reasonable?
So possibly some of the geometry is, especially for neutron star black hole modules, maybe more isotopic. But for neutron star may not so bad. But I never check how is it different.
Yeah, I think some of the models that the numerical model of the mergers of neutron stars usually ends up with a disk.
Yeah, I don't know if it's this green, but yeah.
But I mean, and that disk, though, I mean, I think this might be what Cole is leading to, is that if it's a disk, then the time scale will be shorter if you're looking down on the disk because you have less optical depth for the energy to get out. And so it actually will depend on your viewing angle, which in some ways is good for LIGO because chances are we'll be looking down at maybe an inclination of 0 or 90 to 20 degrees.
Okay. But here I just discussed simplest case.
But it just, I would say that it might reduce your time scale.
Okay. And actually recently macronova candidate was discussed and detected CLD. This event actually happened during gravitational wave numerical relativity workshop at Kyoto. And one day, Ido Ilwaga didn't show up in the meeting. And next day, I asked him, just something exciting detected. At the point, he already started to work on this event. And there seemed to be some, actually this observation I think was done by very important data point is from Hubble telescope. And the PI was Neil Tandier. Let's start. But I think Edo's paper came first, and later Newtonian paper can maybe be some excuse. He wanted to spend more time to write paper, but Edo's paper came first, and he needed to put paper in Astro-GR quickly. Okay. So anyway, this tangent field is quite aggressive, and people just find something, quickly jump in. And this case about in local frame, 7 days later, this is short GRB case, and about 0.1 second, and redshift was 0.36. And basically single infrared data point, people find excess in infrared, basically. And people has optical and X-ray light curve, and if you know the decay, and earlier time they have earlier HSD observation, and if you simply extrapolate later time infrared data point is higher than that, and no excess in optical. So somehow the picture is consistent, time scale, and what we should be seen is consistent with macronova picture. That's why people thinking this is a case actually macronova detected. Okay, so this is so far. Almost, we don't have time. Just quickly, I just want to mention our observation, and 5 minutes or so, and done. So we have Liverpool telescope. It's a 2-meter robotic telescope in La Palma, and the main target is GRBs, and we can through telescope to any direction, okay, as long as seeing sky. Less than few minutes, maybe 100 seconds, 200 seconds after GRB, we can start observation. And that's a good point. But on the other hand, our case, field of view is about 10 minutes. So that case, compared to LIGO error region, that's basically hundreds of degrees square. So it's not ideal to do counterpart search. So what we did is basically PDF did sky survey, and they did about, they also, their field of view is just several degree, square degree or something. And they did basically time observation, and how much? They took about 140 images of tile, and they covered 952 square degrees. So, but this covering about 50% of prior probability that contain two locations. So that indicating quite challenging. And about they analyze correspond to 730 square degree data, and they provided as possible optical counterpart. And we selected rather bright object, more than 20th magnitude, and we did early spectroscopy to identify what they are. So we did about, we follow up about 17 cases, and most case, 7 cases type 1A, and of course they're not related. And maybe 1 case, 2 cases maybe, 1 BC. And AGN is maybe 2. And something interesting is slow moving asteroid is 1. and maybe 3 cases not detected. Maybe the time transients seem to fade away. So this is indicating various things could be happening in transient sky and quite challenging to identify counterpart. But it's quite exciting and people just working on it. Okay, thank you very much.
Any other questions? If not,